All right, good morning, everybody. We're going to go ahead and get started. Welcome. Thank you for joining us. Well, we are breaking records every week with our registration numbers, and this time we've had over 350 people register for this presentation. Thank you all for joining us, for your support of the coalition, and for your interest in building decarbonization. I'm Ashley Spurgeon, and I want to quickly welcome you to today's presentation. And I'm going to make it quick because I'm as anxious as you are to learn from Peter this morning. Thank you, Peter, for sharing your expertise with us. We're so excited to learn from you today. I'm sure most of you are pretty familiar with the Building Decarbonization Coalition, but for those of you who aren't, we are a nonprofit group made up of energy providers, utilities and CCAs, manufacturers, design and construction, local governments, and NGOs, all coming together to work collaboratively on building decarbonization. We have over 160 members all working together to develop solutions to the market and policy challenges of building decarbonization. We have the best members of any organization in the world, and if you're not a member yet, you need to be. So feel free to reach out to me after the presentation with any membership questions. We adopted a roadmap at the beginning of 2019, and in that roadmap, we outlined 5 philosophical overarching goals. These 5 goals really lay out what the coalition thinks are the most critical guiding principles for the state. And the first goal is about building awareness of the issues related to building decarbonization. This webinar series that we put on is one of the ways that we achieve this goal. It helps us raise awareness about different issues and topics related to building decarbonization, and it's a really fun way to spend an hour. This started out as a monthly webinar series, but due to popular demand, it's become a bi-monthly series, and we have some great presentations coming up for you. On July 9th, Bruce Smath and his all-star team, including Holmes Hummel and Gene Clinton, will be sharing the results of their accessible financing project. It's done, folks, and you're not going to want to miss this presentation. 2 weeks later, Rocky Mountain Institute will be sharing their latest report on the air quality impacts of building decarbonization. And then in August, we're going to kick things off with a new product alert. The folks at NeoCharge are excited to announce the launch of their Smart Splitter and tell us all about it. You can learn all about our BDC Presents webinars and other upcoming events on our website, and we hope you'll join us for each of them. So as I mentioned just a minute ago, we have over 350 people registered for this event today, so you're all muted. And we're going to request that you ask all of your questions via the chat feature of Zoom. As you're listening to Peter, please feel free to put your questions and comments into the chat, and I will moderate at the end of the presentation. The recording and slides from today's presentation will be placed in the member portal of our website. This is just one of the many benefits of being a member, and this is the last plug I'm going to make for membership in my 5-minute presentation. So with that, I'm going to stop sharing my screen, and I'm going to let Peter get started. And while he is starting his presentation, I will tell you a little bit about the amazing man we're going to hear speak to us today. So I'm going to stop sharing. Okay. So Peter is the founder and CEO of Point Energy Innovations, a new consulting firm focused on working directly with owners and developers in the U.S. and globally on the next generation of profitable, low-energy, high-performance, and decarbonized buildings and industrial facilities. He has received numerous awards, including the Renewable Energy Innovator of the Year and ASHRA's prestigious Award of Engineering Excellence, which has only been given 4 other times in ASHRA's 100-year history. So today we all have the honor of literally sitting at the feet of the master and learning. Thank you so much, Peter, for giving us your time today.
Thank you, Ashley. It's really a pleasure to be here with all of you today. I appreciate everybody who signed up and took an hour out of your day, maybe, and are here on a Zoom, another one. But I'll try to cover a lot of interesting stuff that's going on. I wanted to start by telling you a little bit of my background and as it relates to this decarbonization thing. I've been working in buildings now for 40 years. And I do remember in the 80s and 90s, there was a big push to get people to use more natural gas. And it was, when our electric grid was pretty much all fossil fuels with a little bit of hydro in there. And in California, we still had even some coal-based electricity. So at that time, gas was actually a cleaner fuel, and there was this whole term fuel switching. So I was part of the push to get everybody to think about using natural gas. And in a sense, I'm doing penance now to try to get people to move back to electric forms of heating. And in fact, it's not, we're going to a new form of electric heating. And I'm going to talk today about heat pumps, which is the efficient form of electric heating. And I think there's a lot of interesting things that are going on right now. I think it's really exciting. So I'm going to try to cover a lot of ground today. I'm going to move a little bit fast and then hopefully save a little bit of time towards the end for some Q&A and discussion. So let me just move right in. The first thing is that if you look at building energy consumption for the US, we still have a very large portion of that building energy consumption is used for heating with fossil fuels. The majority of those fossil fuels are natural gas. In parts of the US, they still use fuel oil and a couple of other things, but the majority of that is natural gas. In California, and I think many of you are from California, there is a more detailed breakdown of our carbon footprint for the state. And this 7% and 5% for commercial, that's for building heating. Notice that electricity is a different category at the top of this pie chart. So a very large part of our carbon footprint is for building heating. And we did a similar graph for the US. It would look very close to this. So the thing that these estimates or these assessments of our carbon footprint don't take into account is methane leakage. And one of the things that Panama, who's the head of the Building and founder of the Building Decarbonization Coalition, likes to say is there's nothing natural about natural gas. Natural gas is methane. When it escapes unburned or uncombusted, it's 84 times more potent than CO2. And what we're finding now is that there's a huge amount of methane leakage at the extraction, at the wellhead. And this on the right is an infrared photograph of one of those natural gas wells with the black is only visible with infrared, but it does show the amount of leakage. And so now the assessments of leakage have changed from 1 or 2% to somewhere in the neighborhood of 4 to 6%, depending on which study you're looking at, but it's in that neighborhood. And that amount of leakage, in fact, doubles the impact, the effective carbon impact of burning natural gas in a building. So when we're looking at these different assessments, I think a lot of them are going to start to change to take into account methane leakage at the wellhead. The other thing about burning natural gas in buildings is, and we don't talk about this a lot, but it's the outdoor air quality of burning natural gas. When we burn natural gas in buildings, it does release nitrous oxide. And in California's cities, that amounts to almost the same amount of nitrous oxide, which is a major cause of smog and respiratory illness. Almost as much comes from buildings as it does from light duty vehicles, cars. And so that's a thing that we're not talking a lot about. There is this carbon impact, but there's also a distinct and important health impact, negative health impact from burning natural gas. So what we want to start thinking about is this path to decarbonize buildings. And I really think the first and most important step is low energy buildings. And I have talked to some people recently who are downplaying energy efficiency. And I want to say, don't downplay energy efficiency, because it's still the most cost-effective way to lower our carbon footprint in buildings. But once we have a lower energy building, then we can move to an all-electric building through heat pumps and other forms of electricity use. And I'm going to talk about that today. And then ultimately, we want to be able to buy renewable-based electricity, either on the building or remotely generated. And many states now have a path, a legislated path to decarbonize the electric grid. Other states, they don't necessarily have legislation to do that, but it's happening anyways, because wind and solar are becoming lower cost than building new natural gas or coal-based power plants. So what do we mean by building electrification? It's using electricity to perform these services, and it's really about the service that we're concerned about when we're working on buildings or working with people who live in buildings. They want hot water, space heat, and cooking. And so there's efficient versions of all of these that use electricity. So I'm going to focus in on heating today, and that's for space heating and hot water heating. And you'll find the majority of heating, space heating, hot water heating is done by natural gas boilers today. And that's where we put in 1 unit of heat to the natural gas boiler, and we get 0.8 or 0.9 units of heat out. And traditionally, we've thought about electric resistance heating. We can buy a little radiator at the hardware store, and electric resistance heating is where we put 1 kilowatt hour in and we get 1 kilowatt hour of heat out. So it's a little bit more efficient, but electricity is more expensive, and substantially more expensive. But there is an efficient version of electric heat, and that's electric heat pumps. And the idea with electric heat pumps is that we use the refrigeration cycle, the same cycle that's in your refrigerator, that's in the air conditioner of your car, or if you live in a building with cooling, it's the same refrigeration cycle that does cooling, just run in a different way. So if you look at it a little bit more closely, of the fuel that goes into a boiler, and we have that 80 or 90% efficiency. The way heat pumps work is we put electricity in, and it's able to pull heat from the surrounding air, and so that we effectively get 3, sometimes 4 times more heat out than electricity that we put in. And that's through the refrigeration cycle. Lots of great videos on YouTube about how that works, and good information on Wikipedia and other sources if you're interested in that. So we'd like to think about this idea of resource to room efficiency. And the idea of that is how much raw energy do we need to put into a system to be able to get, in this case, 100 units of heating energy out. So if we're using natural gas, including losses on distribution and refining, et cetera, for natural gas, it's about 125 units go in to make the 100 units of heat out. If you're going to use natural gas-based electricity with a combined cycle power plant, sort of a new version, efficient natural gas power plant, we only need 74 units of energy in to be able to make 100 units of heat. That heat pump is leveraging the ambient energy. But if we were to use renewable-based electricity, and we don't have all the losses of burning natural gas at a power plant, which are about 50% efficient, we would only need 35 units of renewable-based electricity going in to make that 100 units of heat. So it's a really interesting thing that fundamentally there's just a big shift in the amount of energy that needs to go in to create heat. And I think when a lot of macro studies, not very carefully done macro studies, are done on electrifying the economy at a macro level, they'll say, well, for those 125 units of natural gas, we're going to need 125 units of renewable energy. And that's not the case. With heat pumps and renewable energy together, we're only going to need 1/4 the amount of energy input. And so that's a really, that's a very good news from a societal level. From a carbon perspective, what we're talking about is being able to move to a system where we're creating heat with 0 carbon impact. And when we look at costs, based on where we are today, we've done a study recently looking at the energy costs in a building. This is an office building, sort of standard office building in a wide variety of climates in the US. And what we're finding is the cost of our heat pump heating, although it's more energy efficient, electricity is more expensive, as I said earlier. And so that what that results in is a slight uptick in the cost of electricity. Depends on your climate and your utility rates, your gas and electric rate, but it's usually in the neighborhood of a few % increase in price. To a certain degree, it's in the noise. Weather swings have a bigger impact than the impact of going to heat pumps. So let's dive into the technology, and that's the main thing that I want to talk to you about today is, how do we apply heat pumps and what are the different heat pumps that are available? So let's start by taking a little look at residential heat pumps. The traditional heat pumps have been around for quite some time. I remember seeing them in the 80s on homes where they want an air conditioner, and you can buy an air conditioner that's also a heat pump. It's that refrigeration cycle that can reverse itself. So in the summer months, it's operating as an air conditioner, and the winter months, it's operating as a heat pump. So that's something that's been around for a long time. There's newer systems, this ductless mini split idea, where you have refrigerant pipes going to a fan coil inside the house. That's now available, a wide variety of options there. There's multi-zone mini splits. There's now hot water heaters that use heat pumps. And there are large parts of the country that use electric resistance water heating. So moving to a heat pump hot water heater, still electricity, uses about 1/3 as much electricity to create the same amount of hot water. So there's a wide variety of heat pumps that are relatively simple that are available today for residential. And in large parts of the country, they're already being used. So on the commercial side, it gets a little bit more complicated and there's a lot more options. One thing that we're seeing in commercial buildings is the use of variable refrigerant flow, VRF systems. And we're seeing that take hold very quickly in a large part of the country. I think it's probably the most significant development in HVAC in the last 5 years is the use of this VRF system. And what it does is at a larger scale, it uses the refrigeration cycle to provide either heating or cooling to the building. So you're using the same compressors, you're leveraging the technology that you already need to install in the building for cooling, it can now do heating. And the interesting thing about VRF systems is they're multi-zone, so you could have one zone in heating and another zone in cooling. And in fact, they have a way through the refrigerant to be able to move some of that heat from the area that's in cooling and put it into the area that needs heating. So it's a very interesting and efficient system. The ground source heat pump systems have been around for quite some time. First ground source heat pump system I designed was over 20 years ago, but they've been around for longer than that. In multifamily, like apartment buildings or hotels, this PTAC and PTHP, the package terminal heat pump, has also been around for a while. The difference between today and where we were 10 or 20 years ago is that the equipment is getting better. The compressors that are available off the shelf are now variable speed drive and much more efficient, much quieter than what they used to be. The fans, the same thing. So the technology is getting much better and much more efficient. There's also large air source heat pumps that we'll sometimes use on commercial buildings to create hot water for heating or hot water for domestic hot water. And this photograph here is of an air source heat pump. It just uses the air, is able to pull heat even out of cold air and make hot water. There's heat recovery chillers, and that's used in small and large scale, where if you're in a building that is doing cooling and it also needs heating, we can take the waste heat from the cooling and use it for heating the building. So a good example of that is a building where there's, let's say, a lot of labs or computer rooms or high intensity areas or meeting rooms, classrooms, those kind of things. They all will need cooling, but you might need heating for domestic hot water, or on the north side of the building on a cold day where it's losing heat. So there's lots of buildings that simultaneously need heating and cooling, and we can do that with a heat recovery chiller. So that makes it very efficient. Stanford recently built a brand new central plant, and this is in California, where they have a very large scale heat recovery system. And the tanks that you see there are million-gallon tanks that store hot water or chilled water. So one way they do it is in the afternoons, they might be in cooling and they're making lots of chilled water, sending it out to the building. So waste product is heat. So they'll put it in the tank so that the next morning, when it's a cool morning, they can use that heat that was generated the afternoon before. So they get a lot of, in that climate, they get a lot of sort of warm, not hot, but warm days in the afternoon and cool mornings. So there is a thing about air source heat pumps in cold conditions, and I did want to talk about that. And this is as you start to design buildings that use, this is on the commercial side, use the air source heat pumps. Most of them have different ways of handling when it starts to get really cold outside. So the first thing that happens is when you get down into the 30-degree range, the coil on a heat pump can start to get so cold, the refrigerant's colder than the air temperature, that it can start to condense water out of the air, and then that water can start to freeze. And so that's something that everybody knows about, no big surprise. Most of the companies that have air source heat pumps, they'll have a defrost cycle where they, for a few minutes per hour, they'll run the cycle in reverse and then melt the ice off the coil so it doesn't build up, which then would then block the airflow over the coils and our ability to pull heat out of the air. When they get down to the colder temperatures around 0 degrees Fahrenheit, most of them stop being able to produce heat because it's just too cold. And so a lot of buildings, I work mostly in California, and that's not a problem because we don't get down below 0 very often, if at all, only in the mountains. But I do also work in other climates like Indiana and Georgia. I've worked in Boston, Montana, a wide variety of places. And in those places, we can actually, we'll, for the few days per year that, let's say it's below 0, we can go and use electric resistance heating. Not great, but what we're doing is we're getting the majority of the year very energy efficient, and then a little bit of the year not so efficient. Also, I did want to talk about refrigerants. Most of the heat pumps that are available today, residential and commercial, are using this R410A refrigerant. And unfortunately has a very strong global warming potential of 2,000 compared to CO2, that's pound for pound. And so that's a high level. But now these systems are designed very carefully not to leak the refrigerant. It's very expensive and it's highly regulated. And so I've done an analysis on a 20-year lifetime of a heat pump. And in worst case scenario, if all the refrigerant got leaked, some catastrophic accident, which rarely happens, but it can, we'd still come out significantly ahead with the heat pump, even if all the refrigerant gets out. But if it's managed properly, it's not a problem. The refrigerant can be recycled and then ultimately destroyed. There is a move now to move to lower ozone deplete or global warming potential refrigerants, a lot of companies are going to be very soon moving to this R32 refrigerant, but there's now already companies that have CO2 as a refrigerant. One of them is now making heat pump hot water system that's now widely available in the US. So I think we'll see a lot of CO2 refrigerant machines coming out, but in the nearer term, we're going to see this HFC. There is for larger equipment, if you look at this table on the right, the R1, 2, 3, 4, and a variety of these other HFO refrigerants, their global warming potential is 4. So I think in the larger equipment, that's already available. We're going to see a lot of that refrigerant coming. The nice thing about the CO2 refrigerant is that it's very good on the very low temperatures. It can, the one that's currently available for hot water heating in the US, it's a Japanese company, it works down to -20 degrees Fahrenheit. So no problem with the cold weather situations. So I just wanted to give you a list of manufacturers. There are many, many manufacturers. If you're representing a manufacturer and your name is not here on this list, I apologize. You know, this is just meant to be a sampling, and it's not in any way an endorsement by myself or the Building Decarbonization Coalition, but I just want those of you who are new to heat pumps to understand that there's a lot of companies out there and a lot of options. I did want to end this part of discussing heat pumps with a quick reminder that when we're talking about decarbonizing buildings and electrifying buildings, we are not trying to use electric resistance heating. And this is an example for a 100,000 square foot building in a moderate climate. If you look at the cooling system on the right, it'll have a peak load of about 200 kilowatts. And so we're installing the electrical infrastructure for this 200 kilowatts. If we used an electric resistance boiler for the peak heating load in the wintertime, that's going to require close to 600 kilowatts of heat. It's a lot of heat, and it's a huge impact on the electrical infrastructure for the building. If we use a heat pump system, we're only going to need in the neighborhood of 170 kilowatts of heat instead of this 590. So that doesn't tax the electrical system, doesn't add the extra cost, and it doesn't add of construction. It also prevents very high electricity bills. So I have heard some people say, oh, we'll just use electric resistance. I'm definitely not in favor of that, and feel that there's heat pumps that can be applied one sort or another to all versions of heating that we need to do in buildings. So on commercial domestic hot water, there are smaller, let's say businesses, and these are a little bit bigger on the residential units, the units where the tank comes together with the heat pump on top, but these are small and have limited application. There are the other systems that are meant to be ganged together. They're also small. This particular unit, this is the one that uses the CO2 refrigerant, is used a lot for multifamily, where they gang them together and connect it to a centralized hot water heater. And there was a great presentation about domestic heating, domestic hot water heating with heat pumps a couple weeks ago, the same series. So heat pumps in action. I want to spend a few minutes talking about applications of heat pumps and giving a couple case studies. So the first one is actually my house, where I had a propane furnace that was really at the end of its life. Thank you. Really was happy about that, because it gave me an opportunity to switch over to a heat pump. And this is where I just replaced the furnace with the air handler, and then it's connected with the refrigerant pipes to the outdoor unit, where it's able to pull heat from the outside air. Really happy with it. It's way quieter than my heat pump, than my furnace was, and it heats the house very, very effectively and in a much more gentle, nice way. I've also bought an electric induction stove now, and so my propane tank, rest in peace, is still sitting in my front yard. I'm waiting for the propane guys to come take it. They're hesitating because they're convinced that I'm going to change my mind, which I won't. I want it out of there. So Anyway, I can't wait for that thing to be taken away. We've done a wide variety of multifamily residential projects. This is one for the University of California at San Francisco. It's a medical school. So these are medical students who are living there oftentimes with a spouse. And we did that building with a large central domestic hot water system that uses heat pump water heaters that are placed on the roof. These are the air source ones, and then a series of storage tanks down in the basement. We ran them in parallel, and we do have a recirc loop to keep the lines warm in the building, which does use extra energy, but it is a larger building. And this seems to be working well. It did take some extra time to commission, and that's because this large heat pump centralized system is relatively new in the Bay Area, the San Francisco Bay Area. And so it took a little bit longer. The contractors this was a new thing for them, but it's now working very smoothly. And I think that's one of the pieces of advice that I have, is that you're going to need to spend a little bit extra time tweaking and tuning these systems, because most of the contractors out there are not familiar with this technology, even though these kind of heat pumps have been around for quite some time. It's not like the technology is brand new. There is a weird thing that's happening in California, and that is, and it did come up a couple of weeks ago when we were talking about domestic hot water. The California Energy Code, called Title 24 for commercial buildings, until very recently was not allowing heat pump water heating in any form. And we would have to get exceptions each time we wanted to use a heat pump for water heating. They now have written a letter where they allow the single pass system, and that is a heat pump that can take the cold water in and raise it all the way up to the 140-degree temperature directly and send it right into the building. They don't allow the multi-pass system. Those can be just as efficient as the single pass. It's just a misunderstanding at the state level. And there's this, next version of Title 24, when it comes out in a few years, 2-3 years, hopefully this will get fixed. So I still feel like there is some growing pains of understanding how to apply heat pumps in buildings. And hopefully that's going to get all smoothed out. We did another office building in Menlo Park. Again, I'm based in the San Francisco Bay Area, so my examples are mostly about the Bay Area. So forgive me for those of you who are out of town. I do have a project under design in Montana that's using heat pumps. So in the next time we do this, when that project's further along, I'll put the slides and the pictures of that one in. But this is an office building in Menlo Park. And what we did there is we bought or designed in a heat pump chiller, a unit that can do heat recovery. It can seamlessly switch from heating to cooling, heat pump heating to cooling, air source, and a really nice unit. And when we need simultaneous heating and cooling, it does heat recovery. So that's actually a pretty great thing, to have one unit can do both functions and switch back and forth. One of the things that we do spend a lot of time thinking about and doing in our designs is the buffer tanks. And you can see the blue buffer tank for the cold water, chilled water, and then the red one for the hot water. Heat pumps really like buffer tanks. When you're designing in heat pumps, work with the manufacturers or your local rep to make sure that you're getting the right configuration and the right sizing on the buffer tanks. Really quite important. If you don't have the buffer tanks, heat pumps can tend to cycle, and then that will lead to unstable temperatures as well as premature failure. So it's a very easy thing to design out, but if you don't remember it, it can be a problem. We're doing a large renovation of the building. There were some questions ahead of time about retrofits and renovations. And this building, we're going to be using a couple different strategies. The bottom floor is going to be a big open market hall, and that we're going to have a radiant floor system that leverages the air source heat pump to make hot water. And that air source heat pump will actually be in the garage, and air will, as it moves through the garage, the air source heat pump will be able to pull heat out of that. And then upstairs, where we have an office, we're going to use a VRF system. VRF systems are very effective for office space. We're doing a historic renovation of the building in San Jose, California, and a very important building. And this one, the historic preservation people are in love with us because all the window units that you can see in this picture, the little dots there, but at the bottoms of the windows, those are little window air conditioners. This building was built 100 years ago without air conditioning. And so over the years, people put in little window units and it looks horrible. So all that's going to be taken out, and we're going to be putting in a variable air volume system, a VAV system, very much, you know, a mainstream system. But that VAV system is going to be fed. It's going to have reheat coils. Those reheat coils will be fed with hot water created from a heat pump. So it's a very standard system where we're just swapping the boiler out for a heat pump. The heat pump is an air source heat pump. It's going to have to go on the roof, and but it will seamlessly integrate into what's very much a standard system. So I want to just start wrapping up now and talk about some of the lessons learned. There's definitely a lot of lessons learned, but my top 5 are that the electric technology in the form of heat pumps is ready for prime time. When we're working with these manufacturers, they're telling us that the product that we're specifying has been out for 5 years or 10 years. They've got lots of installations. It's not like we're doing, there's just the very first one. And some of these heat pump systems that we're doing, the technology has been there for 20 years, 30 years, 40 years, just depends. But there's, you know, the technology is ready for prime time. I think that the cost at heat pumps are more expensive than boilers. When we're looking at the cost implications of switching to heat pump, construction costs, for us, we're finding that including labor and everything, it's less than 1% upcharge, you know, in the neighborhood of like 0.5 or 1/4% of total construction to be able to do this. And, you know, that's for, in some buildings, even a 1/4 or 1/2 is too much. But what we're finding is so many of the developers and building owners that we're working with on commercial buildings, once they understand what we're doing, and that is creating a decarbonized building, and they can leverage getting 100% renewable electricity, variety of straightforward ways. And we say this is going to be a decarbonized building. They love that. It's a very simple thing to do. Doesn't make it more complicated or difficult, but it's something that they can tell their tenants or their employees that we're doing the right thing for the environment. The next lesson learned is that the electric systems, you know, in a lot of cases, done right, save operating costs. I did show you one earlier where it was a little bit higher, but that's where we use the same building efficiency. Normally what we're doing with our decarbonized buildings is and heat pump buildings is we're making them more efficient. So we're putting in better, more efficient glass and insulation and a variety of other things. So the amount of heating that we're doing is less, and therefore we end up with lower operating costs. The other thing to remember, in California, we've had recently these power outages, the power safety shutoffs and such in the fall when they're worried about wildfires caused by electric lines. Some people are saying, well, we shouldn't go to electricity because, you know, because of that, let's stick with the gas. The problem is pretty much all gas equipment is now required by code to have safeties and a variety of other things that make it not work, and it won't run without electricity. And that's especially true in commercial buildings. There is no gas heating system that will run without electricity, if nothing else pumps, but they also need blowers for the combustion chamber and a variety of other things. So it's sort of a false sense of security to say we'll stick with gas because of power outage. Now, if we have an all electric building, we can back up electricity. Now with batteries, and solar, that's our favorite way of doing it. But worst case scenario, you can do backup with a generator. Backing up a gas system is very complicated and difficult. because you storing natural gas on site is you know, there's a lot of costs, a lot of regulatory problems with doing that. So I'm generally seeing when I, you know, put these things in front of our clients, and we work for a lot of developers, and they're not always the greenest developers out there. They do see what we're talking about and really do get behind doing the decarbonized building. I did want to end with a little thought piece for those of you on the call who are building designers involved with the construction of buildings in one form or another. And that's a carbon footprint. We did a calculation in our office. I had an intern spend, you know, close to a month working on this to get it right. More than willing to share you the details and all the assumptions, but the average person in the US is responsible for about 980 metric tons of CO2 per year. And if we look at the building designer, our footprint as designer dwarfs our personal footprint. So, you know, don't worry about buying the latest and greatest Tesla. Nice thing to do if you can afford it. But the most important thing you can do for the environment is design low carbon buildings. That's the most important thing. And if you look at it a little bit differently, which is the cost of let's say a designer's education, architect, engineer, construction manager, developer, whatever, you know, let's say in the neighborhood of 100,000 for college, something like that. But the potential impact of energy reduction and carbon reduction in buildings, and if we priced carbon and we're at a very moderate price, it can literally be millions of dollars of savings for one building. Now that's not per year, that's added up over the lifetime of that building. So we're actually sort of underfunding our education because the impact of the work that we do is so substantial environmentally and also financially. So there is a thought that if we really want to solve this carbon crisis, one of the things we should do is create a college tuition program where we're giving scholarships for people to design low energy and decarbonized buildings. So with that, I'll end. And I look forward to your questions or challenges or otherwise sharing experience of things that you've found along the road of decarbonizing.
Well, as usual, we've had a very robust discussion going on during your presentation. Thank you. You inspired so many great ideas and great thoughts while you've been talking. We've really enjoyed listening to you and learning from you. We've had a lot of questions coming in. Some have been answered as you've been talking, but I'll start moderating and see what happens as we go.
Right.
From Jamie, what's the solution for all the existing building stock in the U.S. which is using gas?
Yeah. So in a simple way, it's pretty straightforward. If you take my example of my house, I had a furnace, and you know, when I bought the house, it was perfectly fine. You know, I maintained it, not a lot, but I did the sort of standard things. But it did eventually run out of steam, quote unquote. It was ready to go. That thing was, you know, close to the end of its life. It needed to be replaced. So it was at that point that I would have needed to buy a new furnace anyways that I can swap out to the heat pump. So if you look at it, HVAC equipment, HVAC equipment generally lasts, depending on, you know, which part and maintenance and all these other things, you know, 20 years. It's sort of an average life. Some longer, some shorter. And so if we just say it averages out around 20 years, and then each year, if we were able to change each one of those boilers or furnaces over to a heat pump of some sort, that would mean that we could change 5% per year of that equipment. So the first thing is every day equipment is dying, and we need to plan for that replacement. So I work in a building in downtown San Francisco. There is a roof up there, and they do now have the ability to put, and they already have installed some of these air source heat pumps up there to be able to feed a heating loop in the building. So same thing, they're also starting to install VRF systems on our building. So it does take a little bit of roof space to be able to convert over to the air source heat pumps. Most all buildings in America have no problem. There are some high rises that are going to be a little bit of an issue. But generally speaking, if we plan for it, retrofitting as equipment dies out is the right strategy. It makes it the most cost effective. If we're throwing away equipment that's working today perfectly well, that retrofit's much more expensive as compared to where we're already going to spend $100,000 to buy a new natural gas fired boiler. Let's spend $120,000 and get that heat pump.
So this question from Karen sparked a lot of discussion, but I'm going to throw it to you for your perspective. Karen was asking about a report summarizing the calculation of the GHG impacts of a heat pump if all the refrigerant leaked. Do you know if there's anybody working on a report like that?
No, I don't know of any, macro level study of that. I would imagine that there is somebody looking at that. And, that's why I think that nobody's sort of sitting on their laurels about where we are with refrigerants. I mean, these refrigerants, the first thing that we had 30, 40 years ago is that refrigerants were ozone depleting, and it was having a very, very negative impact on the ozone layer. Now that has been, most of the refrigerants, the ozone depletion potential is either very low or zero. We've sort of figured that thing out. And now it's the global warming potential. And so all the major companies who have compressor-based systems, refrigerant-based systems are already planning, designing, and starting to prototype and build. Some of them are already selling the refrigerants that are much better, like CO2 as a refrigerant. We're going to see a lot of that. And there's the R32 that I mentioned. So yeah.
Okay, from Robert, are CO2 DHW heaters commercially available?
Yes. So the one, and I try not to get into endorsing products or anything like that, but the one that is being sold in the US right now is called Sanden. And I'm telling you that because if you Googled it, it would come up. But Sanden, S-A-N-D-E-N, is a Japanese company, and they have a domestic hot water heat pump heater. And that uses CO2 as a refrigerant.
Okay.
Yeah, and it can be used on a single family home. And it's also being used on small commercial and multifamily when you gang them together. And I showed you a diagram of how they get ganged together.
Great. From Tom, in the SJ Bank of Italy retrofit, will the cool from the rooftop reheat loop heat pump boiler be captured?
Yeah, we set that system up to be really, really simple. So it can use off-the-shelf VV air handlers, package units, which are very popular in the San Jose, Silicon Valley area. And so the only thing we're changing is the boiler over to an air source heat pump. So when we're doing heating for reheat and we're creating cold air, we are wasting that cold air. There is no cool recovery, if you will. We did that because we wanted to make the system simple. If we, there are a lot of, it's a design build project and a, relatively tight budget and everything. So we wanted to just, take it in that direction, but we could have done like what we did on the other building, which is get the heat recovery, cooling, heating system.
Okay.
Yeah.
I have a question from Barbara. I used to do building envelope air leakage testing on older multifamily units with PTACs, and they had high leakage. It sounds like that issue has been solved. Well,
so those PTAC or the PTHP, the one that I showed that goes through the wall. First of all, if you're not very careful, there could be leakage around the unit between the wall and the unit itself. But They also, that's the easy thing to fix or to install correctly. Many of the units that we now have, they also are bringing in fresh air. So if you pressurize the space, fresh air will go out. So it's, it depends on, how you're looking at it, but those things can be done in a way that's efficient. There's a new, and doesn't result in a huge amount of leakage. There is a new unit that's out that has, it doesn't require as big of a hole through a wall. It's more two circular holes, one for air intake and one for air exhaust. And it looks like it could be much tighter from a, air tightness perspective. So I do think that's something to keep an eye on. And if you end up going with that system, because it's very low cost and decarbonized, you do need to put a little bit of extra attention in, how you seal around the unit to the wall. It's a good point.
Okay. From Mark, do you have links to COP versus outside air temperature for residential HP down to -14 degrees Fahrenheit?
Yeah. So, couple things. Again, residential, what they've typically done is that they'll use the standard refrigerants and they'll get it down to like 20 degrees. And then when it's below 20 degrees, they'll have electric resistance as the backup. And so the COP of the electric resistance is 1.0. So, but anyway, the performance data is usually not represented in a curve. They usually would give you the performance data at 40 degrees Fahrenheit and 20, and then 0. So at given temperatures. But yes, all the manufacturers have that data available. It might not be in exactly the form that you want it, but they've got it in one form or another. And I would just, Google or reach out to a local supplier and see what they can get you.
Great. From Scott, for large existing commercial buildings, how feasible is it to convert the cooling system to a heat recovery chiller or other solution to provide electric heat and cooling?
Yeah, I mean, it depends on the building. Generally speaking, from a mechanical perspective, very straightforward. I don't have any problem with it. Sometimes on the very high rises, we've got an issue, and that is we don't have space on the roof for air source and things like that. But I work in a lot of buildings that are in Silicon Valley that are, anywhere from 2 to 10 stories. And those buildings, it's just a very easy, straightforward thing. There's lots of options, and it does depend on, the climate and the building type, building use, building vintage, what the local contractors are comfortable with, those kind of things. So, again, there is a certain amount of discovery that needs to happen for each project, and it's not as straightforward or self-evident as the boiler, because the contractors and the distributors, they know the boilers. They don't even need to call a design engineer. They just say, we need a new boiler, send one down. And when we're switching from a boiler over to a heat pump, there needs to be a little bit more thought into it, because it's a different piece of equipment. It no longer wants to be in the basement only. Some of the gear is going to need to be on the roof. And so, there needs some thought needs to go into how you're going to make it work. I will say that there's some older buildings that use steam. Heat pumps are not good at making steam. Don't ever, you can't go there. The only way you can make steam with electricity is with electric resistance boiler, which I'm not that much in favor of. What they did at Stanford at a high expense is they converted their steam system to hot water system. And then they were able to use the heat pumps. And the heat pumps work best in the 120 to 140 range. And so some buildings have been designed for the peak temperatures at 160 or 180. So it's another thing that needs to be taken into consideration. Lots of buildings are over designed. And so bringing the temperature down to 140 on the coldest day in most buildings or many buildings will be fine, even if it was designed for 160 or 180.
Okay. All right, now we have a question from Alexi. Do you have any idea of the prospects for combination units that provide heat both for space and water? What are the key barriers keeping us from having something along the lines of energy sprung all-in-one applications here in the US?
Yeah. Well, I think the combination units that make, cooling, heating, and hot water all in one, I have seen a few of those out there. I think that as we move forward in this and more people are asking for it, we're going to see that. They are available. Most of those products are available in Japan, where they're very interested in energy efficiency as well as, how do we leverage technology to get there. So that is going to be available soon. The Energy Sprong thing, if those of you haven't heard about it, it's a thing in if I'm not mistaken, just in the Netherlands, where they go in with a whole uh, prefabbed pack that has a heat recovery ventilator and a heat pump and all this different stuff all in one pack, and your inverter for solar, and they put it on the side of the house, put solar on the house, change out the windows, and put some better insulation on it, and your house is now like a net zero energy, 100%, renewable everything. I haven't seen that in the U.S. yet. That we'll see. I think the U.S. is not as focused on these, like, big um, prefab rollout solutions the way they do in Europe. So I don't know if we'll see it go that way here. I think it will be more, this component approach. We'll have heat recovery ventilators, we'll have heat pumps, we'll have solar and inverters, but I don't know if we're going to see as much of all of that come together into one thing. But we'll see. Good business opportunity.
All right, for average single-family dwelling owner with gas hot water heater without solar panels, is there cost savings by changing to heat pump hot water system, or what are the selling talking points for the owner to change?
Yeah, that depends on your climate and utility, and the average homeowner in U.S. It's all over the map. But I think what we're finding is that where we are right now, the heat pump equipment is a little bit more expensive, and in a lot of the climates, the cost is a little bit more expensive to use the heat pump than using natural gas. Again, that's in flux. And you also have to remember, I'm coming at you from California, where we have very high electricity costs. I'm sort of biased in that way. But I think really what we're talking about, and the reason why you want to do it, there's a few things. One is decarbonizing, and that's what we're here talking about today. I think the level of service of the new equipment is much better. I am so much more happy with my heat pump heating system than I was with the furnace. The furnaces are not made to run smoothly. They don't have the variable speed drive. They're not as quiet. They just aren't as sophisticated as the heat pump gear that's now coming out. So there's a quality of service, be it noise or comfort, that can come out of these things. There is the whole health aspect of not burning natural gas in our building. When you have a heater, it actually can. There are lots of examples where the heat exchanger, where you're burning the natural gas and you're heating up water or air to go into your house, that fails, and you're going to get carbon monoxide and NOx in your house, and that can be dangerous. So there's a lot of health and safety things. I don't think that we're looking at right now with this decarbonization at a thing where we're going to see huge energy bill reductions. One of the things that Panama likes to point out is, in new construction, you don't have to install all the extra infrastructure for natural gas. And if we are building a new house that has a furnace and an air conditioner, and we combine that into a heat pump air conditioner, skip the furnace, skip the natural gas piping, in new construction, it can actually be a cost saver on construction costs. So again, that depends on your situation, but in an existing building, it's more going to be, you know, we're taking the furnace out, we're putting in a heat pump instead. Now, if you had a furnace and an air conditioner separate and they're both going to die and you just put in a heat pump instead, there might be a place where that becomes a cheaper solution than having to, you know, replace the two pieces of equipment. But again, it depends. And you know, I think where we are a little bit in the early days of this, like where we were with solar 10 years ago, the early adopters are going to be people who are motivated, or otherwise the code requires them. In California, the code is now starting to require that all new construction and eventually renovations will have to go in the direction of heat pumps. So that's probably the you know, the final solution to get everybody to go there.
All right. Well, unless we have any burning questions that you can't wait another minute not to have answered, we are at the hour, everyone. Thank you so much for joining us. Thank you, Peter, for giving us your time and your expertise. And we will see you all again in a few weeks for our next presentation.
Thank you, Ashley. Appreciate it. And
thank you, everyone.
Everybody for participating.
Thank you,
Yes.
Peter. Great stuff.
I'm going to end the meeting now. Thank you all.